All right, so that's the outline for today's talk, and I will start by recapping of what I said yesterday, and then I will move on to time-dependent reduced density matrix functional theory. So, as I will repeat a few times, the purpose of all this is to get an access to excited state. So yesterday I was talking mainly about only about ground state functional theory. So by like construction, by its nature, it gives us an access only to a ground state, right? It's based on the variational theorem, but we have no knowledge or no way to get excited state. So one of the ways to access a higher part of the spectrum of the Hamiltonian is the time-dependent theory, and I will show you how it's not the only option, as maybe Paul will tell us about, maybe not, I don't know. Paul, will you give a seminar about this? No, okay. But there are some other ideas than time-dependent stuff, but I will talk about time-dependent. Okay, so yesterday I was talking about 1 and 2 electron reduced density matrix and the functionals of one RDM. So as you know already, if you have a density wave function, right, you can easily compute a 1 electron reduced density matrix by taking a contraction of the product of the wave function with the normalization to the number of electrons n. So n, as usual, denotes the number of particles, in our case, the number of electrons. And now, because gamma is Hermitian, you can view it as a Hermitian operator, we can solve an eigen problem for gamma, and then we get an access to, or we find eigenfunctions and eigenvalues, and they have, because of the importance, they have special names. So as I said already, I think yesterday, so the eigenfunctions are called natural spin orbitals, those objects here, right? They depend on the set of position of 1 electron. And the eigenvalues, those lowercase n's, are called natural occupation numbers. And I was also talking about n representability conditions, more about ensemble n representability conditions, and they are put down here. So if you are given a density matrix, you can immediately verify if it's n representable. Recall that ensemble n representability means that there exists an ensemble of states which upon contraction gives you a given 1 electron reduced density matrix, right? So there's a link between an ensemble of states and 1 RDM. That's what n-rep conditions or n representability means. So those are the conditions. You can easily check if your 1 RDM is n representable by checking if the eigenfunctions are, I mean, if it's Hermitian, right? If it's Hermitian, then immediately you have this satisfied that the eigenfunctions are orthonormal. And you have to check the normalization that the trace or a sum of all natural occupation numbers sum up to the number of particles n. And I think those are the most important, the least trivial conditions of n representability, namely that you have the occupation numbers are non-negative and not greater than 1. Okay, that's what we know. And I was also talking about 2 RDM. In general, we can define p particle reduced density matrix given a wave function. So you can generalize this 1 and 2 particle density matrix to p particle by the differences that you are taking a product of psi star and psi, and you integrate this product with respect to p, everything from p plus 1 up to n variables, and then you are left with a function which depends on 2 times p variables. So those are p particle. Of course, as I already mentioned, and probably I will repeat it today, we hardly ever need higher than 2 electron reduced density matrix, for the simple reason that the Hamiltonian for electrons only involves up to 2 particle operators, right? So to get the energy and also other properties, you don't really need 3 or 4 body. But sometimes we do. I will not talk about it, but in most applications or purposes, we just need 1 and 2 RDMs. Of course, in the density functional theory, reduced density matrix functional theory, everything is based on 1 RDM. And this is still a review of yesterday's talk. I told you about the existence of the theorem, which is of Gilbert, which is an extension of Hohenberg and Kohn theorem, which tells us or guarantees the existence of this mapping. So if you are given 1 RDM, it maps or it's related to only one external potential, so only one Hamiltonian, and then if you have Hamiltonian, then at ground state ground state energy is fixed, it's given. So there's a one-to-one mapping between the density matrix and the ground state energy. And there are some constructions of the functionals. This is one of them, a Wallone construction, but it's very formal, and as I said, it's not very practical, right? And then I was going very quickly through some approximate functionals. Actually, I didn't show much, but since there is some interest, I promised I will give a seminar and show the slides that I didn't show yesterday, which will be about functionals, like actual approximations which are available, and what are the theory or the assumptions behind and how they perform, and maybe we can think how we can improve them. Okay, so this is all about the ground state theorem and what we learned yesterday. So now let's move on to time-dependent theory. I will start from very basic stuff, everything that you probably already know, but then I will put it in a different framework, in the framework of density matrix functional time-dependent. So let's start with the time-dependent. So yesterday everything was time-independent. Today, at least in the first part of the talk, we will talk about time-dependent Hamiltonian and time-dependent wave functions and time-dependent density matrices. So beginning with the time-dependent Schrödinger, I have a pointer. Time-dependent Schrödinger equation, we can immediately derive, it's really trivial, a time-dependent equation for the electron density matrix. So for the pure state, what do you do to get the time-dependent equation? You just take a derivative of the density matrix, right? And that's what you get here. And then you insert for the derivatives of the wave function of the state, you insert Hamiltonian acting on the state twice, and the adjoint of this equation here. And then you end up with this equation, which is what? The time dependent of the density matrix. Time dependent derivative of the density matrix is equal to the commutator of the Hamiltonian and the density matrix itself. Okay, probably you already recognize this equation, but I will continue. And before, actually, the name is already here. It's a Liouville von Neumann equation, which is more known in a more general form. So in a similar way, we can, as for the pure state density matrix, we can derive immediately a time-dependent equation for the ensemble state and electron density matrix, and you proceed in the same way as before. So you take a derivative of the state of Ket and Bra, use the time-dependent Schrödinger equation, right, for the time-dependent derivative or time derivative of Bra and Ket, and then you end up with such a right-hand side where you have a commutator of the Hamiltonian and the ensemble density matrix. Okay, so far nothing new. So this is this Liouville von Neumann equation. Now I will write it in a slightly different way, namely using a position more explicitly, right? Using position representation of the state of the wave functions or states. And this is only for a pure state. So we have just one wave function here. And you see, as always, I would assume that the wave function depends on n. It's an n-electron wave function, right, in general. So we have a derivative of the product of psi and psi star, and the commutator. Now this commutator is written down more explicitly. It's Hamiltonian acting on psi star minus psi and Hamiltonian acting on psi. So it's a Hamiltonian acting on psi times psi star and minus the same in a different order. Okay. Now, so it's still the same equation as before. But now let's do the following. Let's skip the primes, right, at n minus p coordinates. Okay, we set them equal to unprimed coordinates. And we integrate both sides of this equation with respect to n minus p coordinates and multiply by this coefficient, by this factor. So if we do it, right, for a given p, we will obtain, let's say for if we do it for p equals 1, so we integrate both sides with respect to n minus 1 coordinates, we will end up, you can check it, verify it easily, with the equation which on the left-hand side involves one electron reduced density matrix And on the right-hand side, there will be a 2-electron density matrix appearing, right? If you integrate this equation with respect to n minus 2 coordinates, you end up with the equation which involves 2 RDM and 3 RDM. 2 RDM on the left-hand side, 3 RDM on the left.
So this doesn't, you mean like depends on gamma 2, gamma 3, or you really mean it depends on the commutator? So it's not a commutator.
It depends on the commutator, right? We always have a commutator of the Hamiltonian and density matrices. Actually, I was a bit sloppy.
Gamma 1 and gamma 2.
Sorry?
So this is not a commutator?
No. So it's a shorthand notation for, which tells us this equation involves, is dependent on, sorry, it's a bit confusing indeed, because I have a commutator. Yes. Right, so the first equation involves 1 and 2 RDM, the second 2 and 3. So you see those equations are coupled, right? And so we obtained a hierarchy of the equations, of the equation of motions for different order density matrices. And this hierarchy has a name, it's, I think, given here, is on top. It's, those letters are after the names of people who were working with those. So Bogolyubov, Born, Green, Kirkwood, and Yvonne. Of course, if you want to solve exactly this hierarchy, right, you cannot just, at least in principle, stop at this equation, because gamma 2 also appears in the second equation and so on. So the cost or the effort to solve this hierarchy is exactly the same as the effort to solve time-dependent Schrödinger equation for the wave function. So it's not really a handy way. But the idea would be to truncate this hierarchy at some level, okay? We can think about it at some level p, and then approximate. So if you truncate after the pth equation, then you have to make an approximation for the p RDM. Ideally, you would like to express it in terms of lower order density matrices, and such efforts or trials have been done by people. Here, there's one reference, but they were not very successful. So what I'm talking about is the idea to approximate higher level RDMs in terms of lower level. It's in principle possible. There are some approximate ways to do it. More precisely, you approximate so-called cumulants so uncorrelated the correlated parts of the density matrices in terms of the lower level, lower order density matrices. This has been tried in time-dependent equations, but the results were very discouraging. I will not talk more about it because I was not involved, but it was like a dead end. But we are not going to do this. We will proceed in a slightly different direction, because our goal is to have an equation of motion, a time-dependent equation, which involves only one RDM, right? The goal is to formulate a time-dependent one electron reduced density matrix theory or equation. So let's see what we can do. So let's take a look at the first equation, this BBGKY hierarchy. So as we already know, the first equation, right, involves one RDM and two RDM, right? And then what do we do? Because we want to get rid, maybe not to get rid, but we don't know this two RDM. So we have truncated the hierarchy already after the first equation, but we can now recall that there is something like a Runge-Gross theorem, and we use this theorem to prove, the proof will be on the next slide, it's very trivial, it's like pseudo-proof, that there is this mapping. So the time-dependent one electron density matrix and the initial state, so T0, we assume that at some initial state, initial time T0, our system is in the state described by psi. Okay, so if you have these two, they determine uniquely a time-dependent RDM, that there is this mapping, right? That's what I will show, the proof of it on the next slide. If this is the case, right, then we can say that time-dependent two electron density matrix is a functional of one electron, of time-dependent one electron density matrix. Okay, so then we will close this equation, right? Because then everything will be a functional, both sides of the equation, functional or functions of one electron density matrix, time-dependent. So now I will show this simplistic proof of this mapping. So let's assume that we have two potentials, right, V1 and V2, time-dependent, and they are different by more than a time-dependent function. Okay? And we assume that they lead to they lead to the same 1-RDMs, time-dependent 1-RDMs, right? So two different potentials and also two different Hamiltonians, time-dependent, but they lead to the same time-dependent 1-RDMs. That's our assumption here. Because if this is the case, it would mean that there is no mapping, right, from time-dependent 1-RDM to the potential. So but if that's the case, then it means that also density, remember, electron density is the diagonal part of the one electron density matrix. So if two density matrices are the same, equal, it means that also densities, the diagonal parts, are equal. But then it contradicts immediately the Runge-Gross theorem, which states what it says here, that if you have two different potentials, then also densities are different, time-dependent densities are different. Okay, so we arrived at the contradiction. So we conclude then that one time-dependent density matrix and initial state, psi 0, they uniquely determine a potential and the Hamiltonian, and then the time-dependent wave function, and as a result, a 2-RDM, time-dependent, right? So we have this mapping from time-dependent 1-RDM to time-dependent 2-RDM.
Is this a sort of time-dependent version of the theorem you showed the last time?
Yes, but it's
the existence of this external potential.
You can see it, but the proof is a bit more complex. But you can find it in the TD in the book on time-dependent DFT. This proof of Runge and Gross, it's quite elementary. I mean, yeah, relatively easy, but I'm not showing it. Yes, but it's an extension of the Hohenberg and Kohn proof to time-dependent case. All right, so we have found out or arrived at this conclusion that 2-RDM, time-dependent, right now it's time-dependent density, 2 electron density matrix is a functional of 1 electron density matrix. And that's what we actually was heading or aiming for, right? We wanted to have an equation of motion for 1-RDM, and that's it. This is it. Of course, the big difficulty is what is this object, right? And you can guess immediately that it's much worse, more difficult to approximate than 2-RDM in terms of 1-RDM for a time-independent case, right? Now we have time dependence. And indeed, there will be, it's an extra difficulty in finding it. Okay, for convenience now I will switch from the position representation of this time-dependent equation to the matrix representation. So we assume it's more a technical thing, let's say. So we assume that we are given a time-independent basis set of 1 electron functions. Those chi p's are functions, orthogonal, time-independent, and we are expanding, representing. There is a t missing here, right? Everything, so the density matrix, this one, gamma 1 and gamma 2 are time-dependent. They are time-dependent, but the basis set is time-independent, okay? So we are switching from position representation to a matrix representation, and in the matrix representation, in the given basis set, the equation of motion takes the form given here, okay? So we have a density matrix, time-dependent, 1-RDM, and also 2-RDM, but now we keep in mind that this 2-RDM, time-dependent, is given by 1-RDM. It's a functional.
Do you have a preferred basis in mind?
Sorry?
Is there a preferred basis for this argument?
Sorry, I didn't hear.
Preferred basis, right?
Preferred, yes. The preferred basis is the basis of the natural orbitals. But it doesn't matter that it's preferred because it simplifies the final equations. They are shorter and easier to implement, maybe. Yes. But in the end, it doesn't matter what basis set you choose, right? It's arbitrary. I mean, you get the same results. Okay, now I will show you now a link because I was at the very beginning today. I told you that yesterday we were considering a ground state, but we would also like to have an access to excited state, to higher part of the spectrum of the time-independent Hamiltonian, right? And then I started talking about time-dependent equations. So what does time-dependent equations have to do, maybe you know this, have to do with time-independent spectrum, or the spectrum of the time-independent Hamiltonian? So the answer is here, right? How can we get or obtain we call those higher states excited states, right? And the differences between the excited state energy and the ground state energy, we call them excitation energies, right? So what's the relation between excitation energies and the time-dependent theory? So to understand it, we have to consider a linear response theory for one RDM, one density matrix. So imagine that we have a time-dependent system, a time-dependent Hamiltonian, and we perturb it with a potential V. So V is the perturbation. Of course, if you add a perturbation, it can be anything, like a light, or we don't even have to specify what it is. Then, of course, a density matrix response, right? There is a change in the density matrix. And in the first order, you can write it using this equation, where chi, okay, there is it's not the same chi as before. Now chi with 4 indices is the linear response function, okay? So if you are given a linear response function, you know the perturbing potential, you can obtain a perturbation to the first order perturbation to the density matrix. For convenience, we can do Fourier transform and like switch from time dependence to frequency dependence, but again, it's more technical. But the important thing is that we know what this linear response function is, right? We can find it easily from the perturbation theory, time-dependent perturbation theory. And you see then, if you do it, then you see that in the denominators, in those two terms, what we have is the frequency of the perturbing potential, right? We assume that there is, like, for example, a field with, which oscillates with the frequency omega. So this is related to the perturbation, but we also have the differences of E0 and EI. So those are excitation energies, right? EI is the excited state, number I. E0 is the ground state. So you immediately see that if the frequency of the perturbation matches one of those excitation energies, right? This is, the whole expression blows up. It's a singularity, or this function has poles at values of omega corresponding to the excitation energies, right? So this gives you like a prescription how we can find excitation energies if we have an axis, or if we compute the linear response function or the perturbation energy, perturbation to the density matrix. So it's easy. So it means that for the frequencies for which this blows up, right, we have singularities. So those frequencies would correspond to the excitation energies, right? So that's why, so we conclude that if you solve time-dependent equations, right? Actually, I will not show now how to solve the time-dependent equations, but we will now derive the linear response equations for the density matrix. If you do it, we solve for the linear response function, then it's easy to find excitation energies because we only have to find the poles of this function. All right, so now very quickly we can derive, actually I think I will be done in a few minutes. Linear response density matrix equations, right? It's standard, it's a standard thing. The biggest difficulty is always to formulate time-dependent equations. But once you have them, you apply a standard perturbation, first order perturbation theory. So you assume that, we assume that the Hamiltonian now is time dependent, but first we assume that at time t0, that's the initial time, the Hamiltonian is time independent, and we are in the stationary state. A density matrix is given, and we, in this derivation, I assume that the basis set, time-independent basis set, corresponds to the natural orbitals. Okay, remember the natural orbitals diagonalize the density matrix. So in the matrix representations, those elements are elements of the diagonal matrix. So with the occupation numbers on the diagonal. but it doesn't, it's one of the possible choices, right? Okay, then we assume that the system is perturbed with one electron time-dependent perturbation. And then we also have to assume a basis set, but so those orbitals phi's are time-independent orbitals, so that's our basis set. And the natural orbitals, time-dependent, are given by this unitary transformation, which is time-dependent. And then we expand, we take a look, we go back to the time-dependent equation for the one electron density matrix, and we expand both the left and the right-hand side up to the linear terms. So it's almost like automatic, right? So you expand one RDM into, this is a zero order term, and this is a first order term. For the Hamiltonian, we have a zero order Hamiltonian elements. And the first order, that's the perturbing potential. And now we have to expand what we have on the right-hand side of the equation. If you remember, on the right-hand side, we have a contraction of 2 RDM, which is the functional of 1 RDM, and the 2 electron integrals, right? So I didn't stop at the definition of those 2 electron integrals, but maybe if you are not familiar, this is the integral which involves Coulomb operator and those orbitals. It's an integration with respect to R1 and R2. So we also have to expand this expression up to linear terms. We expand everything up to linear terms.
Sorry, I'm a bit lost. So why gamma 2 of gamma? Is it again because it's a function of
so
gamma is gamma 1?
Since this Runge-Gross theorem,
gamma is gamma 1 at time t.
Sorry, so
what is gamma?
So this notation means here, right?
Yes.
That gamma 2 is a functional of gamma, right? Okay. But everything is time dependent.
Great. And gamma in itself will be gamma 1, so the one reduced density matrix at time t, right?
Yes.
Because it's a function of.
So it's more subtle. So to find a value, right, of gamma 2 at time t, we need to know full gamma at each time. That's what this theorem
so it's not
tells
only
us.
at time.
It's more.
For every time.
It's not locally in time. This functional dependence. That's the whole problem, that we need to know the full history, let's say, of one electron density matrix. That's what this theorem tells us. To find a gamma 2 at a given time t.
So all the history from 0 to t.
Yes.
Not
from 0 to infinity. From t0 to infinity. You need to know full function gamma of t. And it's not doable, and that's why we have to assume a very brute force or drastic approximation that I will introduce on the next by next slide. But that's exactly the point, that it's an extremely complicated functional, hopelessly, right? Because it's not enough to know gamma 1 RDM at time t to find a value of 2 RDM at time t, right? You need to know full history of 1 RDM, okay, to find a value of 2 RDM required at a given time t. Yes, but it's nice that you asked, because it shows, I hope explains better, or maybe makes you realize how complicated this functional is. It's much worse than in the time-independent theory. Right, so so we expand this expression up to, it's perturbed now, and we are expanding it up to the first order in the perturbation. So we have a 0 order term, which is time independent, and a first order term, which I write in this form. I will come back to this K matrix, show how it's defined. But you can guess that K will be a derivative of 2 RDM with respect to 1 RDM, time dependent. So it's K times first order perturbation at T prime, and we integrate with respect to T prime from minus to plus infinity. Okay, and 0 order terms drops out and so on. And so we are left with the equation which involves first order perturbations to everything that was present in the equation. Now for the convenience, we again switch or change the domain from time to frequency by carrying out the Fourier transform of all terms. And then we use this convolution theorem. This is, again, standard. We end up with such an equation, which is the linear response equation for one RDM in the frequency domain. We could stay with time, but it's easier to work with in the frequency domain. And now you see, that's exactly what we were looking for, right? Because what we have on the right-hand side is the perturbing potential, this V, right? That's our perturbation. And here we have a response of the density matrix, this gamma of omega. It's how the density matrix responds. It's multiplied by this thing, which is the inverse of the response function. Okay? So everything is nice if we were able to, the equation looks pretty simple, but of course the big problem is this guy, this K.
This gamma omega now is the Fourier transform of gamma? Or?
Here, yes.
Sorry. Okay.
Sorry, yeah. So this gamma of omega is the Fourier transform of the response, of the time-dependent response of the density matrix. Right, so you perturb your system. One RDM, one electron density matrix, time-dependent, changes, right? That's the first order change, first order perturbation. Then we take a Fourier transform for convenience to work in the frequency domain. But as I said, we could stick to time deep. At some point, it's no. At some point, it's we have to switch to frequency because it makes the equations simpler. But the difficulty here is this density, the coupling, as I called this object, a coupling matrix. If we had it right, then we would simply find the linear response function. Actually, it's here. And then we would find poles of this function, and here we are. We would have the full spectrum, right? All excitation energies. But of course, it's not as easy because this matrix K, here it's a full definition, which I promised to show. So let's look at what it is, right? So it's a derivative of the time-dependent density matrix times those integrals, but they are time-independent with respect to a time-dependent one electron density matrix. And the first difficulty, of course, is that we don't know this functional, right? That's the whole problem from the very beginning. So what do? I don't know what is the better idea. We only had one idea. We did have introduced the same approximation, which is known in time-dependent DFT, because there's a very similar problem there. Only a similar derivative, only it's with respect to a density. Here we have a density matrix. We take a derivative with respect to a density matrix, time-dependent. So what is this adiabatic approximation? This is a very pragmatic approximation, right? Because we say, okay, we have no idea what this functional is. The only thing that we know is this functional gamma of gamma 2 of gamma 1 for the stationary case, right? Time-independent case. Because we have some approximate functionals and some for the time-independent Hamiltonian. So the idea is let's use what we have, right? So let's use those stationary functionals somehow in the time-dependent equations or frequency-dependent equations. So this is this adiabatic approximation. It's really very drastic. So we assume that this functional is local in time in the sense that the whole time dependency is in this Dirac delta function. Physically, it means that we assume that the system evolves in time, but at each time, t, the system accommodates or achieves a new stationary state. Okay? And then we are free, justified to use a stationary, time-independent functional. Because in the adiabatic approximation, what we need now is a functional 2RDM in terms of gamma, but there's no time dependency here. Okay?
So that is the stationary.
It's a stationary functional, or functional that we have derived or found or approximated, but for the time-independent case. So that's something which we dislike because it causes all kinds of, at least one big problem that I will show. But you see that there is, so now we have two, so this is the approximation, right? Of course, on top of it, we still have an approximation in this functional. Because, as I said yesterday, there are some different proposals for the functionals, but we are not fully happy with any of it. But yeah, so let's continue. I will show you something interesting, that even if we knew the functional, exact functional, because of this adiabatic approximation, of course, we will not get exact excitation energies or excited states. Okay, so due to this adiabatic approximation, a consequence of the approximation is that now the coupling matrix is free of omega, of frequency dependence, right? So it does not involve omega. Because if you insert, right, this expression in the to the integral, right, then you just integrate. This is a time t minus t. You integrate with respect to t minus t, so you get 1 from the integral, and you are left with the derivatives of 2 RDM in terms of 1 RDM. Okay, and now the only, so the next approximation is, yeah, it's given here, but we can skip it because I already said everything. So if we are given, if we knew a functional of the energy, and we have some approximations, or for 2-electron system, we even know this functional exactly, then we can, then immediately we can find this matrix K as derivatives of those derivatives with respect to 1 RDM. It's technical, so the whole, the most important thing is that we have got rid of time dependency or frequency dependency of the density of this coupling matrix. So again, we assume that, in a sense, so the physical interpretation, another physical interpretation, or maybe it's a different view of this adiabatic approximation is that the perturbation is very, very slow. That's why we call it adiabatic, infinitely slow, so that at each time the system acquires a new stationary state or ground state. But all right. So the immediate unpleasant consequence of this adiabatic approximation, it's not that obvious. There has been a lot of debates about it, but it seems that it's true that if you adopt this adiabatic approximation, you immediately lose time dependency or a response of the occupation number. Okay. So you perturb your system, right? That's how you can view it. And then only the natural orbitals response, like react to the perturbation, but not the occupation numbers. So definitely this is wrong, right? Because there should be a response of the density matrix should be that both the orbitals and the occupation numbers change, not only the off-diagonal parts. So you may still be optimistic and say, okay, maybe this is a small thing and we can still get quite reasonable results. And it's partially true, but actually in some cases, as I will show now, we pay a high price for this consequence of adopting the adiabatic approximation, right? So the adiabatic approximation means no changes in the occupation numbers. So we are like throwing away part of the response of the density matrix, but we lose it, we don't recover it. And the other thing is that there is a wrong response in the limit when omega goes to 0. So this is maybe less important for today, but it means that if you derive a response equation to the static perturbation, then the solution, the response of the density matrix, is different from a response matrix from time-dependent equations in this limit omega going to 0. So this is definitely wrong, right? Those two theories should match, right? When omega goes to 0, and they don't. Okay, so now I will show you actually one example for H2, as often. So this is our favorite molecule for studying those approximations. Hydrogen molecule, right? 2 hydrogen atoms, but it's sufficient to see the problem that we have, which results from the adiabatic approximation. So let's just look at black and red curves. So first of all, what do we see here? On the x-axis, this is a bond distance, right? So as yesterday, we are stretching the bond, moving 2 hydrogen atoms apart. When we move along the x-axis, on the y-axis, we have excitation energies. So those are, we can consider those as as energies of excited states of particular symmetry, sigma g. Okay, so the black curves represent exact solutions, right? So this is how the energy of the first excited state of this G, sigma G symmetry, changes. Okay, the first state, the second excited state, and the fourth, and the first, second, third, and the fourth. Okay, and then let's forget about green, because green is DFT. It was only to show that DFT is much worse here than DMFT. So the red curves, yeah, this is interesting, because the red curves are the curves which show, so those are the excited state energies which have been obtained from the exact functional, but under the adiabatic approximation. Okay, so exact functional means that it gives us exact ground state energy, so we like it, right? But now we use this functional in the time-dependent theory with only one approximation, this adiabatic approximation. So this is what I said, we could be optimistic that this adiabatic approximation is not that drastic, but in this case it is drastic and it leads to wrong results. So let's see. So when you don't stretch the bond, right? We are here, the black and the red curves are pretty close, very nice. The error is very small, acceptable. But now if you start stretching the bond, you see the red curve. This is this adiabatic approximation, with adiabatic approximation plus exact functional. It deviates, it's actually, you see that they are missing something here, because suddenly this red curve starts following the curve obtained for the second excited state. So what's going on here? It turns out that the state, the first excited state of the sigma G symmetry, it changes its nature. It becomes so-called it's becoming a double excitation, meaning that the wave, okay, in this region, the wave function is dominated by a single determinant. So that's what I was talking about on the first day. It's like a single reference state. One determinant is enough to describe the state. Whereas in this region, right, this is a double excitation, meaning that you need at least 2 determinants in the wave function to describe it correctly. So we have investigated what is going on closely, and it's purely, like what we have to blame is purely this adiabatic approximation. So the fact that we have got rid of we lost as a result of adopting the adiabatic approximation, we have lost a response of the occupation numbers, okay? So that's what I thought here. No response from the occupation number to the perturbation, so no contribution from the occupation numbers to the linear response function. That's the price we pay. We don't recover this part of the, not part of the spectrum, but we don't recover the part of the spectrum if it's dominated by double excitations.
Because
so
this
it's multi-reference.
double excitations is really a change in the occupation number.
Yeah, it's not, you're right, although it's not, maybe the conclusion is correct, but we showed it, but maybe it's not so obvious. I don't think it's very intuitive. To us, it was not obvious, then we could like really show that it's exactly what it is, right? That if you add the response of the occupation numbers, you would recover this curve here. So that's a problem. Of course, you could say, and the same similar behavior here. I think it's better to see here. As long as the state is not pure double excitation, so it can be described by a single reference, then we are fine. But Okay, the good thing was that TD-DFT was even worse here. But this is an extreme case. So usually the states in chemistry for molecules are not pure. It's a rare case when we have states which are almost pure, like 80%. 50% is also a lot, doubly excited. So, like for example, it's still H2. But now we are looking at excited states of a different symmetry, like spatial symmetry, sigma u. So it's like a different family of excited states, right? And here, though, the agreement is quite nice, right, along the whole, along the x-axis, right? So we stretch the bond and we are still very close. The red curves, this is our exact functional and the adiabatic approximation close to the exact curves, okay? And the DFT, for those who like TD-DFT, you see DFT really fails miserably. In both cases, on the previous slide, you could see it fails. Here, it's the same, maybe even worse. So it's very yeah. So I didn't talk much about TD-DFT, but so TD-DFT is great for some states which are not too much doubly excited, of the double excitation character. And also if you don't have any strong correlation. Here we have 2 electrons, you stretch the bond, so we have 2 electrons which are strongly correlated, we can say. And then the more entangled electrons are, the worse TD-DFT is. But it's because the ground state is already poorly described. Whereas this TD-DMFT, right, time-dependent DMFT, with the adiabatic approximation, stays pretty close. Actually, very close.
Kasia?
Yes.
These 2 different excitations. Is it clear to see that there is time scale differences? Like, because I guess when you do a diabatic approximation, you're assuming that there is really 2 time scales that's happening, right? Or not? So there is supposed to be some fast process and some very slow process, like you were mentioning, and then.
I think it's not really, because here we have time. I mean, this is all linear response theory, right? So we don't really have time here.
But
we don't
correlation
have time scale.
You say it's a delta, which means that you lose. Essentially, you say that okay, I lose my correlation time now. Is this?
No, I think.
Do you understand this or not?
But you understand that we don't really evolve this system in time, right? We only have some time-dependent equations, and then we only look at the response. So adiabatic, you can see it as just a name, adiabatic approximation, right? Because it's valid for, we could just call it an approximation, but it's called adiabatic because it would be valid only if the perturbing potential was infinitely slow. But it has nothing to do. Okay, it has nothing to do to the failure or success of this TD-DMFT theory for the system that I'm showing.
It would matter if you were actually doing the dynamics.
Yes.
But here, in fact, you make the approximation as if you were going to do dynamics. And in fact, then you go back to your linear response, and your time scale is the oscillation is given by the frequency you're interested in. You don't control it.
Yeah. So you could see what I have presented today is you can see it as a way of obtaining a linear response function. So we do it through formulating time-dependent equations, and then we do linear response. But the goal is to get a linear response function. But there's no time evolution here in the end, right? At the end of the day. At the end of the day, we just solve the linear response equation.
So this is what you call your adiabatic approximation, where you kind of just say that there is.
It's even simpler. It's simpler than that.
Exactly. So you're saying
because the approximation is that we are getting rid of time dependency in the derivative.
You're making it static, but then what you're saying is that there is no time correlation also because there's a delta.
Yes.
So
right.
This is what I'm saying. There is no.
Okay. Also,
I'm
maybe
just wondering if,
you see something more.
so what, I'm trying to understand what makes the first image, the picture, like that it's not able to capture the first type of excitations, but it's able to capture the second type of excitation.
Oh, okay, because in the first type of excitation, this matters. A change in the occupation number, or the contribution from the occupation numbers from the diagonal part of one RDM to the linear response function.
But isn't the lack of change in the occupation number, or kind of the fact that it's stationary, say, due to the fact that you made this a diabetic approximation, or not? It is dependent. I mean,
In this particular example that I'm showing for H2, right? It's a special case when by symmetry, I don't know if it explains or maybe confuses, makes it more confusing. So in this case, right, by symmetry, by spatial symmetry, the contributions from the occupation numbers are exactly 0. Okay? They are not there. And we don't have them because of the adiabatic approximation, but it doesn't matter. So if you solve everything exactly, they would not show up anyway. Whereas for the sigma G kind of symmetry, of excited states, they are not 0. They should be there, but they are not because of the adiabatic approximation. I have a feeling it's not the answer to your question. All right, so I'm getting close to the end. So that was interesting because here this is the only case where we can at least investigate what happens, what we get, or how much of the error we have if we use the exact functional, because as I told you yesterday, the only case for which we have the exact time-independent functional is the 2-electron system. So the only approximation, we isolate only the effect of the adiabatic approximation here. And so we see only the effect of the adiabatic approximation. On those plots, we have both the effect of using approximate functional and the adiabatic approximation on top of it, both together. And the results are much worse. Already, this is the same sigma u, right? For those sigma u, symmetry, remember, with the exact functional and the adiabatic approximation, we have very nice agreement for all states of the symmetry, no matter if the bond was stretched or not. But if you use one of the approximate functionals, those BBC2, okay, I didn't explain what it is, but it's quite okay for the ground state. Then the agreement is worse. Which was quite a bad news, because it means that we cannot really do much with the functionals that we have. I mean, it's maybe too much to say that we cannot do much, but at least using approximate functionals, and this is only what we have, right, for systems which include more than 2 electrons, but the error is quite large, and it's larger than from TD-DFT. So the only advantage, I think it's fair to say that the advantage of TD-DMFT over TD-DFT, time-dependent density functional theory, is for cases where we have some strong correlation of the electrons. Then we could hope for obtaining more accurate results, but they would be less accurate than the results from wave function theory. So I don't know. It's also true that this research has been abandoned at some point, and so we developed the theory and we tried a few systems with the functionals that we had at the time, but then it was not followed. I think the interesting problem would be to go back and see if there is a way to have a different approximation than adiabatic, or maybe do something on top of this adiabatic approximation to recover a response of the occupation numbers. This is an interesting theoretical problem also, but maybe it would lead to some improvements of the accuracy of the ground states. Yeah, actually, this is it. So to summarize, like, it was possible to formulate time-dependent density matrix functional theory. Okay, and through this linear response, we can obtain excited state energies. But the accuracy of the data, which is limited, the data already is limited, and the number of systems that we have tried. But what we learned is that the accuracy was limited by the errors both in the resulting from the adiabatic approximations and the approximation and the functionals, right? And we already know that even with the exact functional, the accuracy wouldn't be maybe the greatest, although we should keep in mind what I said, that for like real case molecules, usually we don't have pure doubly excited states. So I would say, what I want to say is that probably the bigger problem is with the functionals than with the adiabatic approximation. This is a more severe problem, the inaccuracy of the stationary functionals. So here I was optimistic. I said double excitations are in principle within the reach, but I meant actually mixed double excitations, not pure double excitations, because those are less affected by the adiabatic approximation. All right, so that's actually it. So I'm done, and as I said at the beginning, I will probably give at least one seminar on it, but it will be more focused on the ground state functionals that I talked about yesterday, and show, like review what has been done in more details than yesterday. Because with TD-DMFT, I said more or less everything that is known, and there is some literature, but much less rich than for ground state functionals. Okay, thank you.